a technical problem. There is very bad communication with people who follow the seminar online. But here we can talk about matters. So Dr. Małkiewicz from Center will talk about Hamiltonian formalism.
Okay, thank you. So it is a pleasure to be speaking here to you. So I will talk about Hamiltonian formalism for anisotropic cosmological perturbation theory, but I will not focus on the theory, on the solutions of the theory, but rather on the derivation of this theory, and the derivation by a very specific method, that is the Dirac method for constrained systems. And I think this offers something new in contrast to what people traditionally do. That is, they always start at the level of Lagrangian and configuration space, and they try to reduce the unphysical degrees of freedom at this level.
Szukam odpowiedniego przycisku.
Okay. This is based on the joint work with Alice Bodrin, who's here in the room. So let's begin with some outline. Okay, so first I will say a few introductory remarks about my motivation. Then I will try to review the Dirac method, but in the setting of the cosmological perturbations. Then I will talk about gauge transformations and so-called Kuchar parametrization. And then all this machinery I will apply to a perturbed Bianchi I universe. And then I will show a specific example how you, by making gauge transformations, how you can obtain very interesting results on gravitational waves in this kind of cosmological backgrounds. And then I will continue. Okay, so as we all know, cosmological perturbation theory is a working model of gravity at cosmological scale. That is, it is used to explain the origin of. That's not tak to nie jest to, co chcę. It's a working model of gravity at cosmological scales. That is, it is used to explain the origin of anisotropies in the cosmological microwave cosmological background radiation. Also, it is used to explain the origin of primordial perturbations in models, such models as inflationary models. What I want to emphasize is that anisotropy actually could play a significant role in the primordial universe. One reason is that it really changes the dynamics, as you will see. Of course, it is more generic model, so it's always better to have more generic models, but there is also some observational data which suggests some kind of anomalies at large angular scales that might require this kind of anisotropic extensions to the usual cosmological perturbation theory. Okay, this is on the physical side, but there is more academic reason for doing this. That is, it provides a simple, the Hamiltonian form of this theory provides a simple, by which I mean manageable laboratory for, quantizations of gravity. You can address some issues which you are interested in, such as quantization prescriptions, the fate of diffeomorphism, invariance and time problem, semi-classical spacetime reconstruction, whether such a notion of semi-classical space has at all any meaning. And in a sense, you can, I think, in this framework is really a very nice laboratory to play with this kind of questions. But this talk is going to be purely classical, and I want to show you a purely classical application of this method. And the application is going to be to study representations of gravitational waves. So let's say first time when we learn about gravitational waves, we learned that they are traceless and transverse parts of the metric perturbations propagating in space. And this is so, but in isotropic space-time. So they are really gauge invariant quantities. But once you go to anisotropic spacetimes, the Hamiltonian constraints include this tensor part of free metric and free momentum perturbations. So it means that in this sector of this transverse and traceless parts of metric perturbations acts gauge transformations. So it means that this representation that we are used to as gravitational waves is not gauge invariant. It's true only in some particular gauge. So it's ambiguous. Okay, so let's begin the let's start talking about Dirac methods first. So we start with the ADM formalism. We define our perturbations as a difference between the free metrics and some background free metric. So this is the free metric perturbation. This is the free momentum perturbation. You also consider a perturbations of lapse and shift, and then you simply expand the ADM Hamiltonian constraint up to second order. So this is all terms that you get. So you have a zero order part and you have a second order part. And so these are linearized constraints, the scalar constraint and the diffeomorphism constraints. And this is zero order scalar constraint. These constraints, so maybe what is interesting is that at first order at zero order, the Hamiltonian itself is a constraint, but at the second order, there is a non-vanishing part. So the second order Hamiltonian is not a constraint as usually as it is in the full theory. And these constraints, linear constraints, they are first class constraints. Up to first order, they satisfy these relations. But also you need another condition for the system to be a gauge system. That is, you need these constraints to be stable under dynamics. So these commutators here for scalar linearized constraint and for diffeomorphism constraint, they have to be zero or at least weakly zero, as in this case. So once you have it, you have a well-defined gauge system. So I assume that the zero order lapse vectors vanish for the models around which I expand. Okay, so what we want to do, want to reduce this constraint system. That is, want to establish a reduced phase space with a physical Hamiltonian. I'm saying a reduced phase space because there's an ambiguity in this. So in this talk, of course, I'm interested in perturbations. So I'll be interested at the perturbation level, but just for the completeness of the discussion, let me start with the background level. So at the background level, we have this zero order constraint. So we have the constraint surface. And then we find some variable, let's call it clock or time variable, such that it will introduce constant time or level sets of this variable will slice the constraint surface given by this equation. And this slicing must be such that the commutator between the constraint and the clock variable has to be non-vanishing. Yeah, here you have to do it for every time because here we have this time problem. We have to include dynamics as well at slightly different situations at the perturbation level. So you have these 4 linearized constraints. You come up with 4 gauge fixing conditions, and now they are put to 0. And the commutator has has to be non-vanishing, or determinant of the commutation relations has to be non-vanishing. And if it's so, you are able to introduce the so-called Dirac bracket, denoted with this D label, which is equal to the Poisson bracket minus this part, whereby delta phi I denote a collection of my second-class constraints now, because now this system forms a system of second-class constraints. So I have 8 second-class constraints.
So what is the difference between H and C?
H. So this is my initial constraint, which I get from the theory, from GR, and these are my gauge fixing conditions. So I'm sorry? Gauge fixing condition, right? Yeah, I will show a picture in a moment, which will clarify these things. Okay, so now once you impose this for conditions, you actually can reduce the number of variables. So you have initially this ADM variables, but you can choose only some of them. The reduced number of variables, so let's call them physical, and then you just put this to 0 in a sense in your in this initial Hamiltonian, and you end up with a Hamiltonian which is physical, and that it generates the right dynamics in this Dirac bracket, right? So you put these constraints strongly because of the use of the bracket. Yes, so this constraint, they generate time transform, diffeomorphism, linearized diffeomorphism transformations. So reducing means you have to somehow so there will be gauge orbits generated by Hamiltonian vector fields generated by these constraints, and the idea is to, for each orbit, a point belonging to the same orbit, they describe the same state of the system, just in different coordinate systems. So the idea is to pick one and only one point for each orbit, and that's what the gauge fixing conditions do. Yeah. Yeah, another way of looking at this condition is that if you just treat it as some function on the kinematical phase space, and this is a constraint function, this is a gauge fixing function, and together with physical variables, they provide a coordinate system in the kinematical phase space. So you can use ADM variables or this set of variables. They are in one-to-one correspondence. So here's the picture. So what you are, so this is the reduction again. For the completeness, I will show you because I think it's nice to see the differences, right, between these two cases. So this is the background level, and this is the perturbation level. So at the background level, you have a constraint here. You have a constraint surface. You have this gauge orbit, and you do introduce slicing by a choice of some time variable. You introduce slicing, and by this you identify this this constraint surface with a contact manifold, that is with something which is equal to the phase space times a real time manifold, right? And there are of course many ways in which you do the slicing. The only thing is that every level set has to cross each orbit once and only once, but they will introduce inequivalent canonical structures to this surface. So that's how this time problem arises. I will come back to this in a moment. So here is a similar situation you have at the perturbation level. So this is a constraint surface given by this gauge fixing conditions, this large C at the perturbation level. Of course, they generate as well these gauge orbits, and your gauge fixing condition introduce this this gauge fixing surfaces which cross each orbit once and only once. And you can do it in many ways. And here you say that actually it doesn't matter. Here it doesn't matter which gauge fixing condition you choose. Actually, this gauge fixing condition, they can depend on time. They can change with time. It doesn't really matter. There is a canonical isomorphism between them. Here, there's always canonical isomorphism between this surface and this surface. The thing is that here you use a larger set of observables, because here you are interested only in observables, let's say, which lie in this surface. And you say that points which lie on this gauge orbit are physically the same. Here, it's not so. So the point here at the background level describes different state of the system than the point here. So you are interested in a larger set of observables which change along the orbits, right? Whereas here you are interested in observables within a restricted set of observables which do not change along the orbits, which we call Dirac observables. So this is a key difference. Okay, a very quick. So this was a phase-space picture, and now this is a space-time picture. What is going on? So by choosing this, so here you have a four-dimensional manifold with coordinates. So we have some time coordinates and space coordinates, and by choosing this time variable, you define the embedding of this constant time submanifolds from the background manifold in the homogeneous universe, right? You introduce the slicing of the space-time of the homogeneous space-time. So this is an internal variable playing a role of time. When it comes to the spatial coordinates, they are external, because you don't have any in this setup. You don't have any fields of variables which change monotonically in space, right, from one space to another. So you cannot use them really to define your internal coordinate system on spatial leaves. So you have to use some external coordinate, and so there is some ambiguity in defining them, but I want to emphasize this thing that you actually work with external coordinates. You cannot introduce internal coordinates in this or approximately homogeneous spacetimes. Here, what you do, you choose this gauge fixing condition, and this gauge fixing condition defines. So there are infinitely many solutions, right? Infinitely many models. So for this, in this background manifold, you can express infinitely many solutions for the homogeneous spacetime, and then for each homogeneous spacetime, there is infinitely many inhomogeneous spacetime solutions. And what this gauge fixing condition do for you? They define an embedding of this constant time surfaces in the inhomogeneous spacetime, and the embedding of this constant x, let's say, manifolds in this inhomogeneous spacetime. Okay. Okay, so here the points which lie in the same orbit, in the same gauge orbits, they define the same state of the system. So what we are interested in actually are the Dirac observables, that is, quantities which commute with the constraints that are constant along the gauge orbits. And now before I showed you, we reduce the system to some set of physical variables, which dynamics we find using the Dirac bracket, but certainly there must exist some set of coefficients such that a Dirac that for each physical variable there is some corresponding Dirac observable such that they are related in this way, right? So this is the usual ambiguity in defining the Dirac, but this is just because this is a physical variable in the gauge fixing surface. So when this condition, this constraint function vanishes, so if you add this gauge fixing function with some coefficient, you will certainly get some Dirac observable. Now the commutator, because now what I'm trying to do, I'm trying to introduce this gauge invariant description. So we succeeded in the reduction of this model to some specific choice of gauge fixing condition and some specific physical variables. But the thing is to introduce gauge invariant description, so I can solve this model once only and for all possible gauges. So what you are using this equality, that is the bracket, the Poisson bracket between Dirac observables must be equal to the bracket between these Dirac observables, but the Dirac bracket in these Dirac observables. On the other hand, these Dirac observables can be related to these physical observables in this way. And of course, the Dirac bracket is blind to these constraints. So you say that this has to correspond to the bracket between your reduced variables. So there is an isomorphism between algebra of the Dirac observables and the algebra of our physical variables. So there must be an isomorphism between all these gauge fixing surfaces and the surfaces and what I call the Dirac space, the space of these Dirac observables. So what you have to do once you obtain your reduced Hamiltonian, you simply make a substitution. What you previously called a physical variable, which describes the state of the system in some specific gauge, you replace it with a Dirac observable. And then, of course, the algebra is the same. The Poisson algebra is the same. So you compute the dynamics and everything using the same bracket. But this already provides you a gauge invariant description. It will be true in any gauge. So, okay, I thought that maybe you disagree with something. No, okay. Okay, and at the end, of course, what you need to do at the end, you need to reconstruct the spacetime. So you do it by studying the stability of gauge fixing conditions. And so this is the gauge fixing condition. So this is the full Hamiltonian, not the reduced, but the full Hamiltonian. This is a problem that you have to use the full Hamiltonian, which is of course very complicated, much more complicated than the reduced physical Hamiltonian. And you have to, of course, impose this condition. And from this condition, you obtain your lapse and shift. This lapse and shift can be expressed as in a particular gauge as physical variables, or of course, these physical variables can be replaced with Dirac observables. So you can have a function of Dirac observables, but this function is gauge variant. That is, it depends, of course, on the gauge which you choose. Then the other thing is that this set of Dirac observables and constraint functions and gauge fixing functions, they provide a coordinate system in your kinematical phase space. So there is so you put this to 0, put this to 0, you choose some values, and you can obtain all the numerical values of your ADM variables. So you can reconstruct your free surface geometry, and you have lapse and shift. So in this sense, you reconstruct all the whole space-time in a given for a given gauge. Okay, but the thing is that this way of, so suppose I want to choose another gauge. The question is, do I really have to go the same route from the beginning, and do I really have to work with this full with this full Hamiltonian, because this object is quite complicated, it's quite long, so doing this computation is really not very convenient. So the question, the intuition was that maybe once you obtain this in one gauge, you don't really need to go back to this full Hamiltonian. You just need to know the physical Hamiltonian to move from one gauge to another and reconstruct spacetimes for other gauges. That was naive expectation, which turned out wrong, but at the end it didn't turn out so bad either. So you can do a small improvement with respect to what I told you before. So you can introduce a new canonical parametrization. So these variables you can make them into the canonical set of variables. I call them Kuchar variables because they resemble this idea of Kuchar for full GR, right? That you make the specific canonical transformation when you have your constraints, full constraints, canonically conjugate variables play the role of internal coordinates, space and time coordinates in full GR, and the rest of the variables are the physical variables whose propagation in these internal variables you study. Here is a different. Here you define in coordinates by putting this to 0. You are defining this embedding, right, of these coordinates. Time coordinates, which is internal, but space coordinates, which are external. So that's the difference. So you obtain because this could be time-dependent transformation in general. So maybe there will be some extra part of the Hamiltonian. And now you can look at the Hamiltonian in these new variables of the full Hamiltonian, how it looks like. So it would look in the following way. There would be a physical part, purely physical part, which depends on this Q and P, which are Dirac observables. So that would correspond to this Hamiltonian. And you would have also a weakly vanishing part. And I included all terms. The terms which are square in this gauge fixing functions is non-existent because otherwise the Hamiltonian constraints, the constraints wouldn't be stable. So you have to remove it on the grounds of a general argument. But you have the following terms. You can think about the meaning of these terms. So for example, if you want to compute for a given choice of gauge fixing condition, if you want to compute the laps and shifts, you will find that this part, which is linear in Dirac observables, gives you the right expression. The lambda free and this part is completely irrelevant. So whatever value you put here, you get the same theory. So from my point of view, this is a completely spurious part. And this is very interesting part because it turns out that this coefficient in the Hamiltonian would be always the same, whatever your choice of gauge fixing condition. So this is actually a gauge invariant part of the Hamiltonian. And this lambda can be related to this algebra. So it comes from this algebra. So we know what is the algebra of constraints in the diffeomorphism invariant theory. We can expand it to any order we wish, and we can obtain it. Just by expansion, and we will find that this algebra will give you precisely this lambda for this gauge invariant part. Okay, so now let's consider a canonical transformation from one Kuchar parametrization to another. So we are trying to find another a gauge fixing condition. Because gauge fixing conditions are canonically conjugate to constraints, you know that the difference is is canonically conjugate to the constraint. Sorry, is that the difference between gauge fixing condition has to commute with the constraint. So the difference has to be a Dirac observable. So you already can find what is the possible. So it's easy to deduce what is the space of possible gauge fixing conditions when the space of gauge fixing condition has to be the space of each gauge fixing condition has to be isomorphic to the space of Dirac observables. That you have to do it at any time because these coefficients lambda and beta in general they are time dependent, right? Okay. So what I want to show you is, because it takes a little bit more time than I thought it would. So you can specifically consider this Kuchar parametrization, but what you can learn from it is that actually, when you go from one gauge to another, which part is missing? Is missing the reconstruction of your lapse and shift, right? Which you need to reconstruct the full spacetime. And you can find that so you compute it for one gauge, let's say your initial gauge, whatever it is. You now go to another gauge and you have to find the difference. And it turns out that this difference, as expected, depends. It's a function of Dirac observables. So here you have linear expression linear in these Dirac observables. But this coefficients depends on the coefficients in the physical Hamiltonian, right? They depends on your gauge transformation, which is given by lambda and beta, right? Here we say that your gauge transformation is dependent on lambda and beta. And it depends on this gauge invariant part, which you can obtain just by expanding the diffeomorphism invariant, the algebra of the constraint in diffeomorphism invariant theory. So in a sense, it is an improvement with respect to the situation when for each gauge you have to start anew the whole procedure. Yeah, there is also another point that you may be interested in various ways of fixing your gauge. You can specify the gauge fixing functions and gauge fixing conditions, but you may also like to impose condition on lapse and shift, and these are synchronous, like in synchronous gauge, and there is ambiguity, and there is a very nice physical interpretation of this ambiguity. Okay, but I don't know if I should go in more details here, or I will start with maybe I will start with the. Do you have any questions? Because I talk a lot. I have a feeling I talk a lot, and but maybe it's clear, or you lost? Sorry.
We are looking at you growing.
With growing interest. Okay. Yes. So what I want to say, I think this is so the interest was to really work out these Dirac procedures in all possible detail in the setup of cosmological perturbation theory. And as you see, you can use it for, you can, well, it does the job nicely. And it also does a job nicely if you try to impose your gauge by conditions of lapse and shift rather than giving explicitly your gauge fixing functions. So okay. So let's go to the cosmological perturbation theory. Okay. So perturb Bianchi I universe. So we consider Bianchi I universe with the line element. So you have three scale factors for three principal axes. You have average scale factor. We include scalar field here as well. So we define our perturbation variables as before. We add scalar field. We defined a Fourier transform of this perturbation variable. So we will work in the Fourier with the Fourier modes. And
what is Q phi Q here in this model?
What is what?
So you use Q phi
Q phi. Where is it? Here? No.
Yeah. What is identification? N, capital N is phi, for instance. AI is Q.
Capital.
What is what?
Capital N. I cannot see capital here. This is the lapse. Yes. This is the background metric, right? So you have only the lapse and you have the scale factors. So this is the homogeneous Bianchi I model.
Okay. So what are Qij?
Qij. Okay. So so this is the full line element of a space-time, which is very close, which is perturbed Bianchi I. So it's very close. It's inhomogeneous, but it's close to Bianchi I, right? So the difference between this element and the background line element is the perturbation variable. Here, it's the canonical variable, which is conjugate to so it's a background momentum, free momentum for the background model. So it's canonically conjugate to AI square, I think. So this is something like directional Hubble rate weighted with something. It tells you how the background space expands in a given direction. Phi?
Yeah.
So we introduce a scalar field to this model. Extra, right? So it's not Kastner model. It could be. You could at the end get rid of it, but I will keep it. Okay. Okay. So after this Fourier transform, you get Fourier modes and the Poisson algebra of the Fourier modes. Okay. It is like conventional and convenient to fix a conformal metric, that is to take this background metric, the Bianchi I metric, and multiply by divided by a squared, and we'll call it gamma ij. And now any rank 2 tensor in this three-dimensional space can be decomposed into these 6 matrices. These matrices, this defines scalar, so-called scalar perturbations. Yes, scalar quantities. These define vector quantities, and these define tensor quantities because
KW are basis of vectors.
Yes. So here we have this wave vector, right, associated with a given Fourier mode, and then and we add 2 vectors v and w, which are orthonormal. So we have an orthonormal frame of vectors, right? And then when I say scalar part, vector part, and tensor part, I'm looking at the way how they transform under the rotation around the wave vector. So this do not change. This change like vectors, and this change like tensors. So it is. So we want to introduce this new the composition of the metric and of the free momenta. So we will introduce with this indices n instead of ij. Okay. Now, the key difference with the isotropic background is that this K, V, and W evolve as gamma evolves, right? In Friedman models, in isotropic models, this is fixed, and these vectors are fixed, and V and W are fixed. Here they evolve. So that's going to be an extra issue with this. So why? So this Fourier transform, we go to the Fourier modes, and this Fourier transform, it fixes slicing of the spatial coordinate system, right? So we have wavefronts of plane waves. And now in the coordinate system, there are just fixed planes. But when you go to the physical space, because you have different rates of expansion or contraction in different direction, this wavefront is continuously tilted in one direction or another, and it's anisotropically contracted or expanded. And this is something which happens here. So you can fix at your initial point everywhere in space. You can fix these bases. You can fix your vector K and V and W. Then, as time passes, and you know how K evolves, but you have to define the evolution of V and W. So this is ambiguity, and there is one way to do it, that you can actually put them at some point, but it can be everywhere in space, right? The homogeneous space, and then you can consider a Fermi-Walker propagation or transport of this basis along null vector field, whose spatial component is dual to this or normal to this wavefront. So it's like you are working with aconal or large wave numbers approximation, and you describe the evolution of this wavefront by evolution of null geodesics. So what you do, you take these vectors, V and W, and you evolve them along this vector. Of course, they would develop temporal components. So you have to continuously project on the space. And once you do it, you obtain such a dynamical law for this evolution. And actually, this choice of basis will give you the simplest possible Hamiltonian, because the Hamiltonian at the end will depend on the choice of this basis. Unfortunately, this is not good when you want to study quantizations and so on, because you will have to be able to solve it explicitly, and very often you are not able to solve it explicitly. So we'll just assume that we will have such vectors that satisfy these laws, dynamical laws, and obtain a simple Hamiltonian. Okay, so it's a pity I can't see the titles of my slides, but I guess there's not much we can do now. Okay, so what we do, we have to choose some gauge, and this is called flat slicing gauge. So you choose some of this. You remember 1 and 2 were the scalar modes. So it's like you assume that at constant, and these are vector modes. So for example, with this condition, you assume that the constant time slices, the metric density perturbation, and the curvature perturbation, the Ricci curvature perturbations vanish. And then you do the things with the Dirac bracket, the completion of the constraints, Dirac bracket, and so on. In fact, this choice is like sort of canonical. It's very convenient because you don't have to actually compute Dirac bracket, because you know what you will get. You have to just remove from the phase space canonically conjugate parts of this variables, and assume that the bracket yes, so you keep only this part, that part of the bracket, which depends on the remaining canonical pairs. That's what you have to do in this case. That's why it's a canonical choice. So once you do it, then you can study, of course, different gauge fixing condition. But your first reduction of the theory usually you want to do in this one, in this theory. So you take your full Hamiltonian and you reduce it to some physical Hamiltonian, and then so what you are left with, three canonical pairs. You remember these are this tensor parts or tensor perturbations of the metric and the perturbation of the scalar field, right? Yes, and the dynamics is simply given here because the Dirac bracket is really simple in this case. Okay. What you have, there's one extra step that you have to do. You have to actually rescale these variables. And after this, your final Hamiltonian, the physical Hamiltonian, is going to be, so I put twiddle on top of this variables to say that they are rescaled with the scale factor. And you get this nice form of the Hamiltonian. So people usually study it in the conformal time. So this becomes A. So you have just one half. You have the usual kinetic part. Then here, what you have the usual. So for each variable, for two modes of the gravitational wave and for the scalar field, you have this gravitational potentials, which when the universe when undergoes accelerated expansion or accelerated contraction, these things become negative, and you have amplification of the amplitude of this perturbations, and that is something which you have already in the isotropic spacetimes, but in isotropic you have this extra few terms which define coupling between different modes of the gravitational waves, different polarization modes, and different. It would be clear why. I mean, okay, it is clear that they have to describe the gravitational waves. Now, this, of course, and this to the other describe couplings between the gravitational waves and the matter perturbations. So even if you start with the universe with no gravitational waves, they will be eventually excited by the matter perturbation. Okay, so this is in a very specific gauge, the flat slicing gauge. So how to go to any gauge? Well, simply rename the dynamical variables. Instead of using this rescaled ADM variables or ADM-like variables, you just put symbols which denote corresponding Dirac observables. I mean corresponding, that is, these are such Dirac observables that when you look at them, confine them to the constant surface, you actually obtain this ADM-like variables. Okay. Here, what it is? This is the set of this Dirac observables. So this Dirac observable. So what I want to to emphasize here. So for example, these two Dirac observables, delta Q1 and delta Q2, they describe two polarization modes of the gravitational waves. Of course, what do we mean by a polarization mode depends on what kind of dynamical equation we put here, right? So the polarization mode is a very ambiguous notion, depends on this basis we choose here. And the dynamics of this polarization modes will depend through this Hamiltonian, which form also will depend on this dynamical law we assume here. So, but in this basis, these are two polarization modes. And what I wanted to emphasize that they, of course, they include the, so they give you a gauge invariant way to compute amplitude of a gravitational wave, right? You have to add with appropriate coefficients the amplitudes of these ADM variables, and you get a gauge invariant quantity, and this quantity and this will correspond to the gravitational wave in any coordinate system that you will use. So they include as well scalar metric perturbation. This would correspond to the density, metric density perturbation, and the whole expression would correspond to the curvature perturbation. So these are also part of this gauge invariant expressions for gravitational waves. When you go to the limit of isotropic part, you will be left just with these things which are underlined. So in particular here, you get this metric perturbations, this transverse and traceless perturbation of metric, unambiguously defining your two modes of gravitational wave, right? But if you work in anisotropic spacetime, and these quantities here, like capital P, VW, they describe the shear of your wavefront. If the shear of the wavefront is non-vanishing, then there are some extra parts, and the concept of a gravitational wave is much more interesting. Yes, so in fact you can just study again. You can study the. So they in fact they depend on the metric, on the scalar metric perturbations, but you can study the behavior under the rotation around this wave vector to see that they really describe two polarization modes of the gravitational wave, and this Q3 and P3 Dirac observables, they describe the scalar perturbations of the field or of the metric. It depends in which gauge you are working. So yeah, so you can compute this lapse and shift, reconstruct the spacetime for this gauge. And in fact, in this particular gauge, flat slicing gauge, the gravitational wave is described by transverse and traceless metric perturbation, but this is not the only possibility. And you can consider something which we call scalar gravity gauge. So what you do in these new conditions, actually, I can kill the one of the degrees of freedom in the transverse and traceless part of the phase space, and I can compute the determinant of the matrix of commutations between this new gauge fixing conditions and constraint functions. And I see that this non-vanishing, it means it's a well-defined gauge, provided that the wavefront is undergoing this anisotropic expansion and contraction. And then I find the expression for what would be a gravitational wave in this particular coordinate system. And in this particular coordinate system, one of the polarization modes will be described actually by scalar perturbation of the metric, which describes the density, metric density perturbation. Right. It is not possible actually to make both polarization modes described by a scalar quantity. But okay. Okay, I will, yeah, so this is my last slide. So here I repeat just my motivation. And here I emphasize the fact, I want to emphasize the fact that this Dirac method, I think, is very nice. You can really give you a very nice way, very clear way to derive this reduced phase space and to play with different gauges and so on. The fact that we work in the anisotropic spacetime, you have the dynamical triad, you have new gauges, which can give you in particular different representations of gravitational waves, and you have much richer dynamics. And something which I tried to tell you was that the structure of the theory is very conveniently displayed in the Kuchar parametrization, and the gauge transformation can be conveniently formulated in this Kuchar parametrization, and the gauge fixing can be achieved in various ways. But at some point, I thought I was going into too much detail, so I skipped. So that's it. Thank you. I'm sorry? Yes.
Is there some transport which is possible to quantize?
It's possible. Yeah, in fact, yeah, this one gives you which one? This basis. So this dynamical law gives you this particular Hamiltonian, but of course the construction of this basis is through this equation, so it's implicit. But you can consider an explicit construction of this basis, in which you will have, if I remember correctly, just one extra term to the Hamiltonian. So I think this would correspond to the simplest possible explicitly constructed basis Hamiltonian. Yeah.
Do you expect this new type of classical or just a reduction from classical one, but with different?
But you mean if I quantize a dynamics of this basis?
Yeah, so basically, instead of classical speech to a classical one,
Yes.
then if you choose a different type of classical, you get a
Amen. You get another classical expression, which is easy to quantize, because you see, because the thing is that these things inside here, they define background. They depend on your phase space. They are phase space expression, right? And you would like to cover it with hats at some point, but you have to know explicitly what is the dependence on the phase space variables. But this you cannot. You will not know until or unless you are able to solve this equations. Yeah, but yeah. So I talked a lot, but I focus on this gauge transformation and so on, because yes, for me this is a very interesting issue. This notion of a semi-classical spacetime that you can quantize in one gauge. You can quantize in many gauges. You can reconstruct semi-classical spacetimes, and then you can compare whether it all depends actually on the gauge you choose. And whether this concept makes any sense, or what kind of sense it makes. So for me, it is a nice laboratory to play with the quantization of this model, and I think this Dirac method really does the job nicely. To connecting different gauges and preparing the formalism for quantization.
Can you tell me what was the role of the scalar field?
What was the role of the scalar field?
Yeah.
Well, it's just matter ingredient of the universe.
It would be gravity interaction with matter.
Yes.
Yeah?
Yes.
Oh. Thank you. And you say that this is a good basis for quantization. Did you do it?
No. It's so it's another. It's the next thing to do, let's say.
Next thing, but when I see these formulas, I'm not sure if it's so.
It is, in fact, it is easy because it's all linear theory. It's linearized gravity, and with this Dirac method, I think we control it. We control it completely. There's of course, at some point you have to solve some dynamical equations, linear equations, but doesn't mean that they are soluble.
And this Dirac bracket, you have explicit form of the Dirac bracket.
Yes, so of course, in general, when you try to compute, it can give you something which is maybe not so nice, but you make a trick of introducing very particular, starting with some particular gauge in which this Dirac bracket is very simple to compute. And this is this one. And once you do it, you just use the fact, which I was trying to explain in the beginning, which is here, that you can actually, when you found it in one gauge, you actually found it in all gauges, because there is this canonical surfaces. So you don't need to compute this Dirac. So Dirac bracket, in fact, it depends on which gauge fixing conditions you will choose. But at the end, it is sufficient to compute it only at one surface, and you know what its form at the other one.
In case of perturbations around isotropic model, you can solve classical, completely. I mean, this canonical framework.
What do you mean solve completely theory? Yes, yes. So this is what was done in this, yeah. I'm sorry?
And in your case,
yes, yes. So that it's completely reduced. So let's say so you are starting with very complicated ADM Hamiltonian expanded to second order, right? And you end up, I didn't show the details, you end up with this or this Hamiltonian, which is already the reduced Hamiltonian, and these are the physical degrees of freedom. So it can be done, yes, it can be done for isotropic, as you say, and so on. So in this sense, it can be solved, it can be reduced. But then solving the dynamics, of course, it's another problem. You can find exact solutions to the Hamilton equations generated by this Hamiltonian. I don't think so. Maybe in Kastner model, but I'm not sure. But even for the background, if you include if you include the scalar field in this kind of background, usually you are not able to solve it. So. Yeah, there is. Yes, so complication is really, so from the point of view of the Dirac method, it's not more complicated than isotropic. The procedure goes in the same through the same steps and so on, and but then you obtain, of course, the Hamiltonian, and the theory is much more complicated. It turns out to be much more complicated to solve the dynamics explicitly. Maybe there are some questions in.
I have a question about this reduced Hamiltonian.
Yes.
So, is it positive definite quadratic form?
No, it is not.
So this is not physical.
The question
Because
was
it's
about the
unstable.
physical Hamiltonian. Is it always, is it positive definite?
Yes.
And no, not necessarily, because this gravitational potential, so-called gravitational potentials here, when the universe undergoes accelerated expansion or contraction, so in case of the Friedman model, it is accelerated expansion of contraction. Here, you look always at the direction, right? Because it will matter in which direction you are looking. So for a given direction, given by this wave vector, you look what is happening to the space. If there is accelerated expansion or contraction, these things will be negative, and it will dominate, and the Hamiltonian can be negative. Yes, it will be unbounded from below.
So this means that the solutions are unstable of this reduced system. Yeah.
Yes, that's the whole idea. That's the mechanism by which you start with your perturbations in the vacuum state, and you end up with large amplitude of the perturbation at the end of the evolution, of the cosmological evolution, because you have this stage of evolution during which the Hamiltonian is negative and the amplitude is amplified.
So, are there questions from this?
So are there other questions?
So I have a question. So can you hear me?
Yes, I can hear you.
Yeah. So there is some result of Fisher and Marsden about the topology of the space of solutions to Einstein equations. And if this Cauchy surface is compact, then around the, so on your picture, maybe if you can show this page 7.
Slide 7?
Yes, slide 7, yes. So I have, so
By the way.
this assumption that
Tu jest, dobra. Dobrze, ale czemu to nie działa? Działa.
yes, so you draw this surface of C equal to 0 as a surface, but in the full theory, full gravity, around the points where there are symmetries, it's not hypersurface, but it's it has conical singularity. So how it's and I have feeling that in your theory, this thing is somehow avoided. So how it happens that you don't see this conical singularity in this?
So sorry, which drawing are you talking about? At the bottom or?
No, at the top. So this C equal to 0. So I understand this dashed line. So in the case when there is a symmetry and okay, you perturb around the some Bianchi cosmology, so there is a symmetry. In the case when there is a symmetry, this surface has a singularity. So it's not a smooth surface. There is conical singularity. And of course, okay, you somehow decompose the mode. So I don't know, maybe there is a way to avoid that. But if you just look at the topology, you cannot, it's not. So
you mean already at the background level, you will see?
No. I mean, if you look for the whole GR, non-perturbative, but just GR. And you're asking what is the structure of the space of solutions before identifying them by the diffeomorphism. Yeah? So the just space of the solutions to Einstein equations.
Okay, I will repeat the question. Yes, so the question is about this constraint surface here. that Wojtek is saying that in full GR, when you consider a constrained surface, there are some conical singularities in full GR. And now his question is, do I have this kind of conical singularities on the constrained surface here? And well, my answer is I don't think so. I cannot see them. So this is just a linear space of linear perturbations. So I don't think there are any singularities here. At the background level, well.
Wojtek argued that those points they exactly correspond to spacetime that have more symmetry. There's an orbital structure.
Right. Right. Yes, I understand. Yes, now I understand. Yes, of course.
But
you would have some. You would expect some singularities, but here you somehow decompose this phase space into the Cartesian product of the background and the perturbations, and so in a sense you also decompose this probably this group of diffeomorphisms and so on in such a way that you avoid the singularities. I think you avoid them. I mean, I'm pretty sure you avoid them. So in a sense, you in this decomposition into the background and the perturbation, you improve the situation, right?
Oh, okay. Yes, probably.
We finish, but we can, of course, you can continue privately.
Okay.
Yeah?